Thank you for the introduction, and also thank you to the organizers for giving me the opportunity to speak in this exciting workshop. So the most talks so far have been either on kinetic equations or time harmonic wave, and so I'm going to talk about time-dependent wave propagation. And the most part of this work was due to my PhD project with Marcus Grote, and is also joint work with Fabio Wille. And so in for wave propagation, in acoustics or electromagnetics or elasticity, waves will propagate any uncertainty about the input parameters over large distances and without much smoothing effects. And this can result in a low regularity of the parameter to solution map. And thus, and in this case, the method of choice are Monte Carlo type sampling methods. And because they're robust to the dimension of the input parameter and also to the lack of regularity. And of course, as you know, multi-level Monte Carlo methods significantly reduce the computational costs and are a versatile, robust approach in a wide range of problems governed by random PDEs, the elliptic ones, and of course, and also wave propagation, as you see in this with these references. So the problem, so the equation we're studying here is the plain time-dependent second-order wave equation, where we consider the wave speed coefficient C here as subject to uncertainty and as a random field, and we consider a bounded domain, and for the sake of simplicity, we restrict ourselves to deterministic right-hand sides and boundary initial conditions. This could be generalized, but the focus is on the uncertainty in the wave speed. And the goal then is to estimate the expected value of some quantity of interest, which related to the solution. And we consider a quite general setting for the quantity of interest, where it maps from the probability space to some Hilbert space. So this could be these could be scalar values, then V would just be the real numbers, but it could also, you could also think as a quantity of interest the solution itself at some fixed time where V would be, for example, H1. For sake of completeness, the basic principle of MLMC is, of course, that you distribute the sampling on a hierarchy of discretizations. So, for example, a sequence of finite element meshes with a sequence of mesh sizes, and for the time stepping, also a sequence of time step sizes. And the idea, of course, is to compute most of the samples on the coarser levels and only very few on the fine ones. And then you can approximate the expected value by the MLMC estimator via the sum of averages over the different levels of these differences. And the accuracy of that estimator is measured by the mean square error, which splits into a stochastic error contribution and the numerical bias. And to bound the error by some error tolerance, you have to choose the number of samples and number of levels in a way that both terms are bounded. And so this is the basic principle. And now we consider a case where, for example, due to geometric constraints, as you can see in this example on the right-hand side, there might be geometric features in the computation domain where the mesh size there cannot be coarsened as much as you want. And in fact, as is illustrated in this 1D example here, this may result in a small region of the computation domain with a fixed mesh size H min overall levels. And for this case of MLMC with the wave equation, this is a bit of a problem. And to understand this, we take a step back and first look at the standard discretizations of the wave equation. So if you take a method of lines approach, you first discretize the equation in space, for example, with conforming finite elements, which results in a system of second order ODEs. And ultimately, you end up with a system like this, where second time derivative of Z plus the matrix A, Z equals the source term. And then you can apply a standard explicit time stepping scheme to this ODE. For example, the very popular and also efficient leapfrog method, where you compute the solution at some time Tn plus 1 from the previous solutions at Tn and Tn minus 1 explicitly. And for this explicit method, the time step size has to satisfy a CFL stability condition, which in this case for leapfrog is the delta t smaller than 2 over the square root of the largest eigenvalue of the matrix A. And this corresponds to a factor, to some factor, sometimes called CFL number times the size of the smallest element in the mesh. And so to, and maybe for some of you, this CFL condition is not so familiar. So I want to illustrate this to you in a very simplistic setting. So here, if you consider a 1D domain in this interval with a coarse mesh of 40 elements and P1 finite elements, so this really very simple. And in this case, the optimal choice for the delta t would be equal to the mesh size H. And then you look at this Gaussian pulse, which propagates inside this domain and bounces back and forth, so nothing very interesting. And if you increase, say, the time step a little too much, so 5%, what you see is that very quickly you see that the method becomes unstable and you get oscillations in the solution, and you don't see anything of the true solution anymore, but simply these oscillations. Now move on to a slightly different example, where now we take 2 of these previous coarse elements and refine them by a factor of 2. So now we have 38 coarser elements and 4 finer ones. And now we first do the wrong thing and take the same time step as before. And what you see is that immediately you get the drastic explosion of your numerical solution, exactly where the local refinement is located. And if you take a time step that is already significantly smaller, it doesn't help at all. The solution still explodes. So you really have to choose delta T proportional to H min, no matter how small the part is where the local refinement is. And then the solution remains stable. And this now back to the MLMC setting is a problem, because this means that here in this case, we have to take a tiny time step size on all levels. And this this is a significant problem for the MLMC, for the multi-level approach, because now it's computationally very expensive to compute the samples also on the coarser levels, because you have to use a tiny time step because of the CFL condition. And the idea to solve this problem is to use local time stepping, where basically you adapt the time step to the local CFL stability constraint. And for notation, so per one global time step proportional to the coarse mesh size, we do basically P local time step in the refined region. And now, so overview of the fully explicit local time stepping we're considering here is the one which was introduced in 2009 by Julian Diaz and Marcus Grote, which is a fully explicit leapfrog-based local time stepping method. And this method conserves the discrete energy, and also a multi-level, multi-tier version was then developed, which basically allows for, if in your mesh you have several tiers of, say, mesh sizes, you can have multiple different time step sizes in the domain. And this approach was also tested on an HPC architecture and achieved high parallel efficiency there. But there are also versions based on the same idea on other standard time stepping schemes. So for example, Runge-Kutta as well. And for this method, in 2018, Grote, Milling, and Sauter proved the optimal convergence under a CFL condition. However, under CFL condition, which actually depends on the number of local time steps. So essentially on H min, which and this is due to some weak instabilities that are possible for certain values of delta T, which I will explain in more detail in a moment as well. And very recently, last year, we were able to prove in this paper optimal convergence for a stabilized version of this method under a CFL condition, and also error estimates independent of the number of local time steps P. And although this is not directly connected to MLMC, I want to talk quickly about these developments around this stabilized version. So the original method, the basic idea is to split the vector of unknowns into the unknowns associated with the coarse part and the ones in the refined part. And then you get this algorithm which proceeds via a three-term recurrence relations, where per global time step delta T, which is then proportional to the mesh size in the coarse region, you have P local time steps with a smaller time step size. And from the computational cost point of view, you have P matrix vector multiplications with this matrix AP, which only affect the unknowns in the locally refined part, and only one multiplication that also affects the unknowns in the coarse part here in the beginning. And this method can be rewritten in a compact form. So for one global time step, with this global update matrix AP, which can be written in terms of Chebyshev polynomials. And for the method to be stable, the eigenvalues of this matrix times delta t over 4 must be in the open interval 0, 1. And for a discrete set of critical delta t's, these become equal to 0 and 1, and there the weak instabilities are possible. And this is why we use the concept known in the parabolic context as damped Chebyshev polynomials, where you introduce a stabilization parameter, which replaces the Chebyshev polynomials by a scaled version, and then you can replace the matrix AP by a corresponding matrix AP nu. And this results in the stabilized LF-LTS algorithm, which is quite similar, a little bit more complicated, but also very similar to the previous one. So the main features are still the same. So I really copied these two lines from the previous slide. So this is still from the computational point of view, you still have these three-term recurrence relations with these matrix vector multiplications, where most of them only affect the unknowns in the refined part. For p equals 1, the method is completely equivalent to standard leapfrog. And for nu equals 0, we recover the original method. And the same algorithm was also developed independently by the group of Hochburg at KIT. And for this method, we were able to prove this optimal convergence independent of the number of local time steps. So this was the end of the excursion on theory of local time stepping. So to come back to our UQ problem, so we now we use this method, for which there are now also rigorous convergence proofs with finite element methods to this problem. And it seems already quite obvious that using local time stepping will improve the efficiency of MLMC compared to using a standard method, standard time stepping. But we're now so. But the question is, of course, how much do we gain, and in which parameter regimes the gain is largest, and for this we take a look at the detailed cost comparison. So we consider the total cost of the MLMC estimator for a given error tolerance epsilon, which is I think quite well known in the community. And now we estimate the increase of costs for MLMC with a standard time stepping over local time stepping. Maybe I must also comment here. I write leapfrog and leapfrog local time stepping. This is so this analysis here of this cost comparison really is not dependent on the standard scheme on which the local time stepping is based on. So this really also the same analysis also holds for, say, Rangakata based local time stepping or the leapfrog type methods of higher order. And this increase is then estimated via this theoretical speedup, which is just the ratio of the two costs functionals. And this speedup mainly depends on the dimension of the computation domain, obviously, on the parameter R, which is the relative volume of the locally refined region compared to the whole volume. P0 is the, and also on P0, which is the local refinement ratio on the coarsest level of the, and then you get this kind of monster of a formula, which we want to take a look on, or based on the single parameters. And for the example which we had earlier, so where you have a geometry, where you have a small fixed region in your geometry, where you have local refinement. In this case, this speed up is constant with respect to the error tolerance. So there is no change in the asymptotic complexity or something, but you get, nonetheless, you get significant constant speed up factors. So for example, and what you can see here is now the speed up with respect to the relative volume R and the local refinement ratio P0 for 1D, 2D, and 3D. And so maybe let me stop here at this 2D. So it's well, pretty obvious, you would say, that the smaller the relative volume of the locally refined region, the larger the speed up gets, and so yeah, and so for and if you consider the speed up relative to the local refinement ratio P0, in that case, it's maybe a bit more surprising that the speed up is largest for intermediate values of the of this local refinement ratio. So for example, here in 3D, I think the optimum is somewhere in between 20 and 30, and this is not as surprising if you look at the speed up, just if you forget about multi-level and anything, you just consider local time stepping on a given grid on a single level, then and you perform the same cost analysis and also compute the speed up. And if you plot this relative to the local refinement ratio, you get quite similar curves here. And so this was local refinement in a small fixed region. And now we also want to consider another example. So, another reason why you might have local refinement in your mesh is due to singularities, or if you consider like L-shaped domains like this. There it is well known that also for the wave equation in general, uniform meshes like this will not yield the optimal convergence rates, which was studied on in this work by Müller and Schwab. And a ideal solution to this problem is to use a priori graded meshes with a grading parameter S, where S equals 1 corresponds to a uniform mesh, and the larger S gets, the more the elements are clustered near where the singularity is located at the reentrant corner. And in this case, we analyze that there are cases in which the speed up may even increase as epsilon goes to 0. So the asymptotic complexity can in fact change. This is, I must admit, this is limited to only a certain parameter regime and in certain cases, but even if you're not in these cases, you still will have the analysis from before, like constant speed up factors. So for example, so to show you an example of the thing we showed, so for example, if you consider a special example in like 3D s equals 2, if you perform this analysis, then you would get the cost complexity like this for standard time stepping, and for local time stepping it looks like this. So for example, if beta was, so the ratio for the variance is less than 17/4, then you see that here you have different rates. And for example, for P1, so for second order method in the L2 norm, for example, the speed up would grow as epsilon to the -3/8, which is not an extreme rate, but still significant, I would say. Okay, so now let me show you some numerical examples, which are kind of proof of concept of what I showed you. So, so the first two are 1D, and then after that, there's also a 2D example. So in 1D, so the first example we're looking at is piecewise constant wave speed, where there is a jump somewhere, but the exact location of that jump position is considered random. And here on the left, I'm not even sure if you can see that here on the slide, not really. You see different realizations of the wave speed, where we actually chose a variance which is actually very small, but still, if you look at the corresponding solutions to the wave equation, you can visibly see the different solutions already. And for this example, we then compared the computational cost, either using the local time stepping method or not using it. So using a standard scheme here in red or in blue. And in this case, you get a speed up factor of about 3, I would say, which is, say, a moderate gain. But there are also more extreme cases. So for example, if you consider this continuous velocity with this Carnot-Liouville expansion, here the speed up we got in this example was a factor of about 30, so where the using local time stepping with MLMC was 30 times cheaper than the standard method. Okay, so surprised how much time I have. So I can talk in detail about this 2D example. And here we go back to the original domain, which we saw earlier, where we have this these two rectangles, which are connected by a very narrow channel. And now we assume that the exact width of this channel is random. And we look at the wave equation, weak wave equation, just with a constant coefficient here. And now you might ask, well, at the beginning, he said we are on a deterministic domain and random coefficient, but this can actually be reformulated by using a geometric transformation from a reference domain with a fixed channel width. And then you can reformulate this problem in terms of random coefficients on the reference domain. And so for the discretization, here in this case, the mesh size on the coarsest level is 1/60. Here in this in the rectangles, and inside the channel, the mesh size is like this, which results in a ratio of about 22. And then we consider this initial condition, this initial wave, where we have this pulse, which is centered in the middle of this of the right rectangle, and then it will propagate into and hit the channel. And then the question, of course, is what will happen then? And I hope I can show you. Let's see if this works to show you this as a short animation. Maybe it doesn't. Sure if this works. If this doesn't work, but apparently it does not work. Yeah, so sorry. Actually, I wanted to show you this did not work the way I intended. So previous presentations I had always had on my own computer. So what you would see is that actually only a very small percentage of the wave actually passes through the channel. And most of it gets reflected at the entrance of the channel. And so if you look at one specific realization, after a fixed time, the solution will look like this. And here on the right, you see a zoom in of the left half of the domain. And as you can see, so here the maximum amplitude is less than 0.5, and here it's something like less than 0.02, so way less than 5% of the amplitude here compared to the right-hand side. And now we apply multilevel Monte Carlo to estimate the mean solution along this dashed vertical line in the left half of the domain at some fixed time, and as a root mean square error tolerance, we have a root mean square error tolerance that corresponds to about 2% relative L2 error, which is, I think, a decent error, not too large, and yeah. In this case, so since already on the coarsest mesh, the mesh was already quite fine because of the wave needs to be resolved. In this case, we get in total 4 levels, so 3 refinement levels, so capital L equals 3. And here you can see so for certain realizations of the random of the width of the channel. You can see different solutions along this dashed line. And in blue, you see the final estimate. And in this case, we got that MLMC combined with local time stepping results in the estimator being computed 6.8 times, about 6.8 times faster than with the standard scheme. This concludes my talk. So as I showed you, so locally refined meshes will, for the MLMC method, will lead to increasingly stringent CFL condition on coarser levels, which significantly reduces the advantages of the multi-level approach. But local time stepping can greatly improve the efficiency of MLMC in presence of complex geometry. The method remains fully explicit and also inherently parallel. And with a detailed cost comparison, we quantified the gain between the two approaches, and for graded meshes, LTS can improve the overall complexity. So possible extensions. So of course, especially in case of graded meshes, of course, it would be interesting to look at combining this with this multi-level, multi-tier local time stepping. There, the advantages would be much more, I think, and also general. I think this could be relevant for MLMC combined with adaptive strategies. So thank you for your attention.